So today, lesson 41B, ratios and unit rates. So we're beginning a new unit today. And a lot of today's lesson is review from 6th grade stuff so that we can then extend that out to the 7th and then the 8th grade stuff. All right, so let's get started. A ratio, which you should have talked about last year, is a comparison of two numbers with usually similar units. So an example of that might be something like this: 4 boys to 9 girls. And sometimes we have diagrams to determine ratios, and this would have been one way that you would have looked at it last year. So here we have 4 boys compared to 9 girls. And that's an example of a part-to-part ratio. And this is where we need to start filling some things in. And there are a few ways of writing that actual ratio. Typically, we like to write ratios as fractions. So 4 over 9, that's one way, and we should continue writing here. The second most popular way of writing a ratio is with a colon. So 4 colon 9. Some other ways might be 4 to 9. Or maybe 4 out of 9. Once again, the fraction is the most popular way of writing a ratio. Colon is the second most popular way. And today, we'll, in most problems, we'll be writing them both ways there. So one other way of looking at that specific ratio would be 4 boys out of 13 total students. And where I got 13 total students is adding the number of boys and the number of girls together. I suppose we could have also thought of it as 9 girls out of 13 total students. And that's an example of a part-to-whole ratio, because 13 is the whole number of students, or the total number of students. And if we thought about that in terms of a table, it might look something like this. So our original ratio that we were given were 4 boys to 9 girls. And if we continue with that ratio, multiplying both number of boys and number of girls by 2, we get 8 out of 18, and so on. And these, of course, are all equivalent ratios. They're all equivalent to 4 out of 9. And then we could make a third row there by taking now a look at total number of students. So I'm just bringing this up because these are things that you would have done in the 6th grade. Okay? So more examples of ratios. 3 for every 2. We could write that as 3 over 2 or 3 colon 2. I'm going to stick with the two most popular ways of writing ratios. 4 out of every 5. We could write that as 4 over 5 or 4 colon 5. 7 to 8, we could write that as 7 over 8 or 7 colon 8. And of course, 7 parts to 3 parts, we could write that as 7 over 3. Notice how I did not write that as a mixed number. We typically write ratios as fractions or with a colon. All right, so we're at number 1. Please simplify that ratio as a fraction and then with a colon. Go ahead and try that. So 40 out of 35, or 40 over 35, that's just a fraction. If we simplify or reduce that, we get 8 over 7. Remember, don't write that as a mixed number. Write it as a fraction. And then as a colon, that would be 8 colon 7. All right, could I get all of you to go ahead and do 2 through 7? I'll get back to you in a couple minutes and we'll compare them. 2 through 7. Number 2, we started off with 16 over 12. That, of course, simplifies to 4 over 3. That's what that ratio would be simplified. And then with a colon, 4 colon 3. Number 3, started off as 36 out of 42, which as a fraction is 36 over 42. But that simplifies to 6 over 7. And then with a colon, 6 colon 7. Number 4, 24 to 6. As a fraction is 24 over 6, but that simplifies to 4 over 1. And with a colon, that would be 4 colon 1. I don't know what I just did right there. That's if we're doing that, but I'm choosing not to do that. Okay, there we go. 9 cups of flour for every 6 eggs. As a fraction, that's 9 over 6, but then we need to simplify that, and that simplifies to 3 over 2. And with a colon, that ratio is 3:2. Number 6. 6 parts per 27 parts. That would simplify to 2 over 9, and then with a colon, that's 2:9. And then our last one of this bunch, 20 apples to 25 oranges. As a fraction, that simplifies to 4 over 5, and then with a colon, that is 4:5. So that was a quick review of what we mean when we're talking about ratios. Now, rates. A rate is a ratio. We're on the back side now. I think we have some blank areas that we're supposed to fill in. A rate is a ratio that compares two quantities that are measured in different units. And when we talk about different units, we're usually talking about units that have little to do with each other. The last problem mentioned apples and oranges. Well, they have something to do with each other. They're both fruit. Okay? We're talking about boys and girls. We were talking about students. When we're talking about different rates, we're talking about two things that have very little to do with each other. Like 38 miles for every 2 hours. Miles is distance, hours is time. They are related with a formula, but really very little else. Here's another example of a rate, and we should be writing these down. 50 meters per 5 seconds. Here's another one. It cost her $82 for 4 tickets to the movies. These are all examples of rates. Or maybe this one. The car was driven 124 miles on 5 gallons. So I'm going to stop for a second to let everybody get caught up. Now, one thing I want to make clear here, these are all examples of ratios as well, because a rate is a ratio. But since we're talking about things that have different types of units, there's a more specific name for that, and that is a rate. But talking about rates, we're more concerned about a specific type of rates, and this would have been a type of rate that you would have talked about last year, and that is what we typically call a unit rate. And a unit rate is a rate that compares quantities in different units, so just like a rate, because that's what a rate is, but it has a denominator that is equal to 1. It's a rate that compares quantities in different units and has a denominator that is 1. In other words, you're trying to find how many for every one. How many for every one? How much per one? Or for each one? And there are lots of different ways of phrasing that. But the idea is how many for each one, how many per one, how much per one. Or so many of y per 1 of x. The idea is we're trying to make sure that the denominator is 1. When we simplify, and so on. And how we usually find that is we divide, typically to find the unit rate. That's usually the easiest way to figure out what the unit rate is. And tomorrow we will see the importance of that, more so than maybe today. Okay, so a quick review of what we talked about so far. Ratios. We usually don't write the units. You know, if you go back to all of 1 through 7, we didn't really write any units. But rates and unit rates, we usually do write the units. Because we're trying to figure out how many dollars per pound, or how many miles per hour, or something like that. Okay. So a couple of examples. If we were given 1,575 words in 25 minutes, that is a rate, by the way. But if we're trying to figure out what that is as a unit rate, we would need to divide that. 1,575 divided by 25. Notice how I wrote it as a ratio first, but I'm showing off to the side how we get there. And 1,575 divided by 25 is 63. So we write our unit rate, and we need to have units there, 63 words per minute. Okay, now it is a unit rate. 1,575 words in 25 minutes, that is a rate. But 63 words per 1 minute or per minute, that is now a unit rate. Here's another example. 432 miles on 12 gallons, that is a rate. It's not a unit rate because we're trying to figure out how many miles for 1 gallon. And to figure that out, we would need to divide. And when we divide, that divides out to become 36 miles per gallon. So 36 miles per gallon, or for 1 gallon, is the unit rate. 432 miles on 12 gallons, that is a rate. Okay, so there's a difference between rate and unit rate. All right. Everybody, please find the unit rate for 8, 9, and 10, please. 8, 9, and 10. 84 students in 4 classrooms. As a unit rate, that would be 21 students per classroom. I see some of you writing it like this. And that would be fine. I mean, this means the same thing as this. It doesn't matter to me as long as you write something that tells us truly what the unit rate really is. How many students for 1 classroom, or how many students per 1 classroom or per classroom? Number 9, $30 for 8 lunches. Number 8 came out nice and even. Sometimes they don't. Sometimes we just have to divide to figure out really what that is. And 30 divided by 8 is 3.75, so it is $3.75 per lunch, or $3.75 for 1 lunch. Number 10, 16,000 cars sold by 2,000 dealers. That is an average of 8 cars per dealer, so that is the unit rate. All right. A quick review between all 3 of those things that we just talked about, ratios, and I know we have some blank areas that you need to fill in here, so make sure you're paying attention to where you are. 20 inches to 3 feet as a ratio, that would be 20 inches over 36 inches, and that simplifies to 5/9. We, of course, could write that with a colon as well. 300 miles for 5 hours, that is a rate. If we want to find the unit rate, we would need to divide that to figure out what that would be. That would be 60 miles per hour. Ratio is a comparison of 2 numbers. A unit rate is a comparison of a number to one in different units. Notice in the ratio example, we have similar units there. They're both measuring distance, and then I was able to convert them actually to the same thing. For ratios, it's always written as 2 numbers, most of the time as a fraction, sometimes with a colon, like 3/2, 4:9, 15:1. In a unit rate, the denominator must always be 1, because you're trying to figure out how many per 1, how much per 1, and so on. For example, 30.7 words per minute, or 3.5 children per family. For ratios, we usually don't need the units. For unit rates and rates, we always write the units. For ratios, we reduce to simplify. For unit rates, we divide to simplify because we need the denominator to be equal to 1. And so then that leads me to our last little thing here, and that is this. Money usually goes on top of our original rates. And so we're going to do a little bit of a comparison of that in our next problem. So money usually goes on top. Not every single time, but most of the time it makes more sense. So if you look at number 11, the statement is 8 oranges for $2. 8 oranges for $2. The question is, well, one question is, how much does 1 orange cost? How much does 1 orange cost? I'd like you to figure that out. Now, of course, most of you can do that in your head. How much does 1 orange cost? 25 cents, right? And the way to get that is it's $2, and this is when I say money usually goes on top. Most of the time it makes more sense for money to go on top, and in this one it does. So $2 divided by 8 oranges, 2 divided by 8 is 0.25. It's not 4, by the way. So that's 25 cents per orange. Another way of not having to write the word per, if you look up here, I have the slash. That's probably the easiest way to write a unit rate if you use the slash in there. But there are times where we might be asked to find the unit rate the reverse way. Money usually goes on top, but not every single time. So now I'm asking you, how many oranges can you buy for $1? Because sometimes that might make more sense. If you only have $1 and you want to go buy as many oranges as you can, how many oranges can you buy for $1? 4, right? So that's taking a look at it in the reverse way. And sometimes we are asked to find the unit rate in both directions. And sometimes you're going to be asked which way makes more sense. Okay? It all depends on the scenario. So we can buy 4 oranges for $1. Or 4 oranges per $1. Okay, number 12, please. Find the unit rate. 5 tickets cost $87.50. Find the unit rate. So we're trying to find the unit rate. So it makes most sense to figure out how much it is for 1 ticket. So this is a perfect example of when I say money usually goes on top. This is a classic example right here. So how much does 1 ticket cost? Well, we would have to divide that to figure that out, and as I think all of you got, $17.50 per ticket. So let's think of this for a second, reversing it. All right? Does it make any sense if I reverse it to figure out how many tickets you can buy for $1? I mean, think about that. So the previous problem, both directions made sense. This one, it doesn't really. So there's really only one real direction to go with this to figure out one that makes sense. The unit rate that makes most sense is to figure out how much it costs for 1 ticket, not how many tickets you can buy for $1. Okay? So the real reason why we need unit rate is coming up in just a second, but really quickly I'd like you to turn to your shoulder partner, and I would like you to discuss what we've talked about so far, but here are the 3 things we've talked about. In your discussion, I want you to discuss the similarities and the differences between those 3 things. Go. All right, I heard lots of good discussion there. Ratios, one of the things I heard, don't necessarily need units. That's true. Both rates and unit rates do need units. That's true. You can think of, if you want to, as the unit rate being the simplified version of a rate. In some respects, that kind of makes sense, but the problem with that definition is that a unit rate, we're trying to figure out how much it is for 1, so the denominator always needs to be 1. So just simplifying may not be a good enough definition between rate and unit rate, okay? All right, so why do we learn about unit rate? Well, mainly for lots and lots of real-world problems like the one that's coming up here for number 13. So the question for number 13 is, which is the better deal? 20 ounces of orange juice for $1.35 or 1 quart, which is 32 ounces of orange juice for $2.40. This never used to be the case, and you guys are not old enough yet to go out and do grocery shopping on your own, but now the latest thing over the last year or two is now the unit rate is posted on a lot of items when you go out, so that it takes all the brain work out of it, especially at Costco. Costco, for almost every single food item you buy, it'll have the unit rate right in small font compared to what the price is, but it kind of breaks it down for you to figure out what the best buy really is. So the better deal here is going to be the cheapest one, or the smallest amount per ounce. So if I found the unit rate, and I'm going to do this one for you, if I found the unit rate for the first scenario, $1.35 for 20 ounces, divide that, that would give me 6.75 cents per ounce. In the second scenario, and I rounded it to 7 cents because if you were to go buy it, that's what they would charge you, because it rounds to 7 cents. In the second scenario, finding the unit rate, we get 0.075, so 7.5 cents per ounce. If you were to go to buy that, they would round that to 8 cents per ounce. So obviously the better deal is the one with the smaller unit rate. That would be the first one, $1.35 for 20 ounces. That would be the better buy in the long run. Okay? All right, so now you are going to do number 14. And number 14, and I'm leaving this up here because I know people are copying stuff down. Number 14 states that I don't know why it says an 22 ounce. It should say a 22 ounce can of soup costs $1.45. A 20 ounce can of soup costs $1.29. Which can of soup has the best price per ounce? Go ahead and figure that out, and then we'll compare with our shoulder partners. When you're doing your division, you really don't need to go out more than 3 decimal places, because we have to round to the hundredths place because we're talking about money. But once again, I tried to make this one really close. So $1.45 for 22 ounces gives us this. I actually went out 4. So that's 7 cents per ounce. That's what you would be charged. And the other one would give us 6 cents per ounce. So the better buy, or the best price per ounce, is obviously the second can of soup. All right, we are finished for today.